Kinematics is a fundamental concept in robotics. It describes the motion of robotic systems without considering the forces that cause the motion. In simpler terms, kinematics is the study of how robots move. This field is crucial for understanding and controlling the position, velocity, and acceleration of robot manipulators. Robot manipulators are like arms with joints. These joints allow for movement in different directions. Kinematics helps us determine the exact configuration of these joints to achieve a desired position and orientation for the robot's end effector. The end effector is the part of the robot that interacts with the environment, such as a gripper or a tool. Forward kinematics is a fundamental concept within robotics. It involves determining the position and orientation of a robot's end effector based on the given joint angles. Imagine you have a robotic arm with two joints. By knowing the angle of each joint, forward kinematics allows you to calculate where the end of the arm, the end effector, will be located in space. This calculation is essential for controlling the robot and planning its motions. For instance, if you want the robot to grasp an object, you need to know the precise position of its end effector to guide it towards the object. Let's consider a simple 2-DoF manipulator. This manipulator consists of two links connected by two revolute joints. Imagine a human arm with only a shoulder and an elbow joint. Each joint can rotate, providing 2 degrees of freedom. By knowing the length of each link and the angle of each joint, we can easily determine the position of the end effector in a two-dimensional plane. This calculation involves basic trigonometry. Visualizing forward kinematics becomes easier with diagrams. Imagine a 2-link arm, where the first link is fixed and the second link can rotate around the first link's end. The position of the end effector is determined by the lengths of the links and the angle between them. This can be visualized as a triangle where the lengths of the links are the sides and the angle between them determines the position of the end effector. Section 5. Reverse kinematics, from pose to joint angles. Reverse kinematics is, well, the opposite of forward kinematics. Instead of calculating the end effector position from joint angles, it determines the necessary joint angles to achieve a desired end effector position and orientation. Think of it like this. You know where you want the robot's hand to be, and reverse kinematics helps you figure out the angles of all the joints to get it there. This is important for tasks like path planning and control, where you define the desired trajectory of the end effector, and the robot needs to calculate the corresponding joint movements. Section 6. Challenges of reverse kinematics. Multiple solutions and more. Reverse kinematics is more complex than forward kinematics. One reason is that there can be multiple joint configurations that result in the same end effector pose. This means there might be multiple ways to position the robot arm to reach the same point. Another challenge arises from the non-linear equations involved in solving reverse kinematics problems. Unlike forward kinematics, which involves straightforward trigonometric calculations, reverse kinematics often requires more sophisticated mathematical techniques. Section 7. 3 degrees of freedom, a more complex case. Moving to a 3-DoF manipulator increases complexity. This manipulator adds another joint and link, allowing movement in 3 dimensions. Solving for reverse kinematics here often involves geometrical approaches or iterative numerical methods. These methods help find the joint angles that satisfy the desired end effector position in 3-dimensional space. Section 8. Applications of forward and reverse kinematics. Forward and reverse kinematics are essential for various robotic applications. In industrial settings, robots use these concepts for tasks like pick-and-place operations, welding, and painting. By knowing the desired position of the end effector, reverse kinematics enables precise control of the robot's movements to perform these tasks accurately. In surgical robotics, these concepts are crucial for minimally invasive surgery. Surgeons use robotic arms to operate with precision inside the human body. Forward and reverse kinematics ensure that the surgical instruments reach the target location with minimal damage to surrounding tissues. Section 9. Conclusion. The importance of kinematics in robotics. Kinematics, encompassing both forward and reverse kinematics, forms the bedrock of robot manipulation and control. It enables us to understand and command the motion of robotic systems, translating desired end effector positions into specific joint configurations. Mastering these concepts is essential for developing and utilizing robots across various domains, from manufacturing to healthcare and beyond. As robots become increasingly prevalent in our lives, a strong grasp of kinematics will be paramount for engineers, programmers, and operators alike. The future of robotics hinges on our ability to effectively analyze and control the movements of these sophisticated machines, and kinematics provides the foundational framework for achieving this goal.